Hello, class. This is Mr. Hart. In this podcast, we want to finish up the last part of the circuits unit, and that is going to deal with the idea of equivalent resistance. Okay, and the reason why we talk about this is because we often talk about circuits as if they only have like one resistor in it. Okay, like when we did Ohm's law, for example, we said the voltage is this and the resistance is this. Right? And so what's the current to the circuit? Okay? So we always kind of treat things like they only have one resistor, but in reality, these things have lots of resistors in them, right? So think about even like a computer, for example. I mean, that thing has billions and trillions of resistors and, components to it. So it seems kind of silly just to talk about something that only has one resistor in it, okay? And so it actually turns out that that's okay, but we have to realize it's the idea of what we call equivalent resistance. Okay, so instead of finding out these quantities for every single individual resistor, okay, we can treat all these resistors together, add them up in such a way that we get what they would be if they were just one resistor, their equivalent resistance, right? So I have all these resistors in this circuit, in these devices, right? But I can add them all together in such a way that I get their equivalent resistance, or what they would be like if they were just one resistor. So before we get into why these things behave the way they do, let's do the math first, just because I want to get the math down, and then it'll be easier to kind of talk about the concepts that go along with it, okay? But there's two main types of resistance, okay, or resistors. There's resistors in series or in parallel. And as you saw in the lab last time, how we set up resistors in series and parallel, okay? But they kind of build on each other in different ways depending on whether they're in series or in parallel, okay? So let's look at the math for both, and then we'll talk conceptually about why that is, okay? So if we set up the resistors in series, okay, it's really easy how to do the math, okay? So the equivalent resistance, this Req, okay, as we write it, so R is always resistance, right? And I need to learn how to spell this one day. Resistance. Okay. And then EQ as a subscript means equivalent, or basically total, right? The total resistance, or the equivalent resistance, is just equal to the resistor or resistance of the first resistor plus the resistance of the second resistor, and so on for all the resistors that are in series. Okay. So again, recall that in a circuit, they're in series if they're in line with each other. Okay. They don't go off on a different branch, right? If that was like one of our circuits, for example. Okay. All of these resistors are in series. They're on the same line of the circuit. So if that's the case, you just take the resistance of each of these, okay, and add them together. Okay. So we'll come back to that in a second, and we'll talk about why that is, but let's just do some example problems first. Okay. So a circuit contains 4 resistors in series. Each resistor is 200 ohms. What is the equivalent resistance for the circuit? Okay. Really easy. Okay. The equivalent resistance is just 200 ohms for the first resistor, plus 200 ohms for the second resistor, plus 200 ohms for the third resistor, plus 200 ohms for the fourth resistor. Okay, or basically 200 ohms times 4, which gives you a total resistance of 800 ohms. Okay, so if I was building this circuit, okay, and you had 200 ohm resistor, 200 ohm resistor, 200 ohm resistor, 200 ohm resistor, okay, and all 4 of those resistors were 200 ohms, okay, that would be equivalent as far as the current goes, okay, as having one resistor that's 800 ohms. Okay, so if each of these guys was a 200 ohm resistor, okay, this circuit is equivalent as far as current. The current and the power consumption, okay, are equivalent to a circuit that just has one resistor that is 800 ohms. Okay, that's what it means. So we can treat this circuit mathematically the same way we treat a circuit that has just one resistor that's 800 ohms. Okay, that's what it means as far as equivalent resistance. Okay. All right, let's do one more. Okay, again, this is really easy. Go ahead and try this on your own really quick. You might be able to do it in your head by the time I finish reading this. But what is the equivalent resistance for this circuit? Okay. And so we see that we have 250 ohms for resistor 1, 750 ohms for resistor 2, and 250 ohms for resistor 3. So 250 plus 250 plus 750 gives you that's the same as 250 ohms of resistance. Okay. And there you go. So really easy to calculate. And again, now we can treat that circuit as if it's one resistor with 1250 ohms of resistance. Okay? Alrighty. That's for in series though. In parallel, it gets a little tricky. Okay? Because now you have multiple pathways for things to travel through. You get this equation right here. Okay? So this is equivalent resistance for resistors in parallel. Okay? So now the equivalent resistance is equal to 1 over the first resistance plus 1 over the second resistance, and so on. So remember, a parallel circuit is one where the resistors would break off onto multiple lines, okay, like this. So these resistors would be in parallel. Okay, it looks something like that. Basically, now the electrons have multiple pathways it can go through. And so instead of the resistors helping each other to increase the resistance, now they're kind of fighting against each other, because now they're kind of letting electrons have more options. So now the electricity is going to flow faster if there's more resistors. So this kind of makes sense, right? The more pathways you add, the less resistance you would expect overall, okay? Because there's multiple outlets, okay? But anyways, this is a weird equation because it's one of the only equations you see in math where, or not math, but in physics, where your variables stays on the bottom like this. Okay, so I'm going to show you how you can fix this on your calculator, or how you can type this in on your calculator in just a second. But just keep this in mind. It's kind of odd to have the equivalent resistance on the bottom of this equation. Okay, but it's how it's written. And because we can think of it as these things adding so that they hurt each other rather than help each other, like in series. All right, let's go through an example problem, then you'll see how this works out. Okay. So a circuit contains a set of 4 parallel resistors. Each resistor is 200 ohms. What is the equivalent resistance for the circuit? Okay. So because these are in parallel, we're going to have to add them in terms of the parallel equation, or on the bottom of the fractions. Okay, so 1 over the equivalent resistance is equal to 1 over 200 ohms plus 1 over 200 ohms plus 1 over 200 ohms plus 1 over 200 ohms. Okay. So in this case, because all the bottoms are the same, which is nice, we can add these tops together just like you would do in a regular fraction. So we get 1 over the equivalent resistance is 4, 1 plus 1 plus 1 plus 1, over 200 ohms. Okay. And then if you simplify that fraction, you get 1 over 50 ohms. Okay. So then in this case, the equivalent resistance, since these are both on the bottom, Req equals 50 ohms. Okay. So this one works out nicely because these are all the same. We can just simplify the fraction and then take what's on the bottom of each of these. Okay. Doesn't always work out that nice though in other problems. Okay. But look at this. Keep this in mind, right? We have 4 200 ohms resistors, right? But instead of adding together to get more resistance, right, because they're in parallel, you're allowing multiple pathways. Now you end up with a smaller resistance, a much smaller resistance than you started with, okay, 50 ohms. Okay. Now you may be asking, why in the world would you want to do that? Okay. And it turns out it can be nice in certain cases because you may need exactly 150 ohms of resistance, but you only have 100 ohm resistors. So you can put them in parallel and some in series so that you can get the resistance values that you want. Okay. So this is more for design's sake, where you would want smaller resistance values if you're trying to get a specific resistor value. Okay. All right, let's look at a more tricky example where you don't have such nice numbers to work with. Okay. So what is the equivalent resistance of this circuit? So now we have 250 ohms, 750 ohms, and 250 ohms in parallel. Okay. So if we're trying to find the equivalent resistance, we do 1 over the equivalent resistance, or Req, equals 1 over 250 plus 1 over 750 plus 1 over 250. Okay. So there's two ways you could do this. You could try and find a common denominator, times these both by 3 to get the same base value. But I'm going to let you use your calculator if they're not the same. Okay. So let's try this. Okay, so what I'm going to do first of all is I'm just going to do 1 over 250 plus 1 over 750 plus 1 over 250 in my calculator like this. Okay, so just add them as straight fractions. Okay, and then you should be able to get just like a decimal. Okay, a decimal value like this. Okay, so what I would do is I would just say, okay, well, as a decimal, 1 over Req equals 0.00933. Okay. So if I want to solve this equation, it's very simple, right? I just take Req to that side, divide by that decimal, and I get that Req equals 1 over 0.00933. Okay. So we just do that in our calculator. 1 divided by 0.00933. And that will tell you that the equivalent resistance is equal to 107 ohms approximately. Okay. So I'm okay if you're not exact on this. You're welcome to use your calculator on the parallel ones. Okay. So the equivalent resistance equals 107 ohms. Okay. So just for parallel, just write them out as fractions like this. Get the decimal value on your calculator. Okay. And then do 1 over that value to get the actual equivalent resistance. Okay. Awesome. So again, you kind of see the same thing though. We have these huge resistors right here, or anyways, bigger resistors compared to this. You put them in parallel and you get something that's a lot smaller than them. Okay. Awesome. But there we go. So that's pretty much it for resistance. Let's go through one more example though, where you have both series and parallel. Okay. So if you ever see series and parallel resistors first, usually you're always going to want to do the parallel resistors first, right? So if this is the same as last time, right, we found by adding these in parallel that this was 107 ohms, right, total, okay? So now I can treat this whole block right here as 107 ohms. So then I can do these guys plus this guy, or sorry, this guy plus these guys plus this guy gives me the series value, so it would be 300 ohms plus 107 ohms plus 300 ohms. So the total resistance for the whole circuit is 707 ohms is the total resistance. Okay. So if you ever see series and parallel in the same set, okay, usually you're going to do the parallel first and then add it in series. All right, so that's how we do the calculations. Now let's actually think about why these equations work out, what's going on here, what's happening to the electricity physically when we're going through these circuits. Okay, so let me go back to just series first. Let's think about series by itself really quickly, and hopefully this makes a lot of sense that the more resistance you put in a series, okay, the harder it is to get through, right? Or the more it's going to slow down, okay? Because it's kind of like, let's say you have to climb a hill, okay? And when you climb the hill, okay, as you're climbing it, as soon as you get to the top of that hill, you have to climb another hill, right? So same thing with electricity, right? Electrons have to climb this hill or go through this resistance with this resistor. And then as soon as they get to the top, they're like, oh, hey, there's another hill they have to go through. So then they have to go up that hill. And then when they get across, they have another hill they have to go through, right? So overall, they're going to get slower the more resistors they have to go through, right? So hopefully that makes sense. I don't have a whole lot of analogies for series. I think it's pretty intuitive that the more resistors you add in the line, it's just like having one resistor that's a lot steeper, right? So going up 3 smaller hills is the same as going up a much larger hill, right? So hopefully that makes sense intuitively. But let's think about parallel to kind of give you an idea of why parallel makes sense, okay? Let's go to this hill analogy. I think I gave this analogy when we were first talking about resistors. But let's say these electrons are now going down a hill. Okay, so either way, they're trying to climb up the top to the top of the hill. But let's say they have 2 pathways they can travel. Okay, if they only have one pathway, let's say this 100 ohm resistance, let's say the hill's very shallow, so they can go down the hill a lot faster, right? The steeper it is, the harder it is to climb, so the slower you have to travel, right? So if there's only one pathway, all the electrons have to go down that pathway, right? It's going to be pretty shallow. They're all going to be able to take it just fine, okay? But let's say there's a second pathway now, which with a much higher resistance value, right, or a much steeper hill, okay? What you'll find, okay, is that most of the electrons are going to want to take this route right here, right? Just like most humans would want to take that hill because it's shallower. But there's always going to be that one crazy guy that's like, hey, I'm totally just going to face climb this thing and go down this value. I don't want to wait in line with all the other electrons to get down the hill, right? There's this other pathway. I'm going to take it, okay? So that means there's less people that have to go through this pathway, right? So overall, the resistance for this whole hill is slightly smaller, okay? Let's say it's 98 ohms. Because now these ones are less crowded because now there's a new pathway they can take. If the resistance value is a lot higher, less of them are going to take it, so it's not going to change the resistance value a lot, but it is going to allow some electrons to go through that pathway, okay? And you can also imagine if there was a second hill that was a lot shallower, right? There was one that went this way that was, around the same value, okay, or same shallowness. Then about half the electrons are going to want to take this pathway, and half are going to want to take that pathway, right? So overall, the resistance is a lot less, right? Because now there's another pathway, more of them can take it, right? So overall, the resistance is about 50 ohms. Okay, it's less crowded, that type of thing. Okay? So that's kind of in parallel. When you allow more pathways, more options, some electrons can take those new pathways, and so now the overall resistance or the ability for the electrons to get through changes. Okay. Let me give you one more analogy to kind of help you think about this. All right, so let's relate resistance to shopping line, for example. And I know you've all done this, right? You've all done this at Walmart before, where you're like, do I go on the line with a really slow checker and the lady has like 50 items in her cart, but it's only her in the line, or do I go on the line that has like 10 people, but they all only have one item, right? You always kind of make a guess, right? And then you usually pick the wrong line, it seems like. But anyways, let's relate this to resistance, okay? So let's say that we have resistors, and they're basically the checkers, okay? So something with a low resistance is a checker that goes really fast, right? You can check out people really quickly through the line. Whereas a high resistor is something that resists a lot, right? So they're really slow, which means they can only check out they check out a lot slower, right? So if you think about it, if you just had this one resistor, okay, again, it's kind of the same idea, all the electrons have to go through it, right? So that total resistance would be the resistance of the checker, right? 100 ohms, okay? Then let's say you open a second line up, okay, then it's a lot slower, okay? Most people are going to still stay in this line, though, because they know that it moves faster, right? So electrons, likewise, are going to stay in this line, right, or stay in that pathway because they know they can get through faster, okay? It's less resistance. But again, there's going to be that one electron or that one person that's going to take the slow checker just because there's less crowding, right? There's space, that type of thing, right? So there's now a new pathway. So the total speed or total resistance for both lines would be a little bit smaller, right? So it's about 98 ohms, okay? It's kind of the same idea with the ohm analogy, right? But again, this is for resistors in parallel. If you open up another line, the total resistance goes down, right? Maybe a little bit, maybe a lot. If this resistance or this line is like 50 ohms, right? He goes even faster than a lot of these guys would jump to this line because now it's going to go faster for them, right? Electrons do the exact same thing. You put in a 50 ohm resistor, most electrons are now going to jump to the other resistor, go through that because it's less resistance. Some will stay with this one, but overall the total resistance is going to be less than both of them combined, right? Whatever it is. I'm just making these numbers up, but you get the point, right? Adding up multiple pathways in parallel allows the electrons more options, so the total resistance is always going to be smaller, okay? That's why we have to use this equation, right, where they get smaller instead of bigger when we do equivalent resistance, okay? That's where it comes from, okay? All right, so just remember those two equations. In series, it's just adding them straight across. In parallel, you have to add them as a fraction, okay? And hopefully you just kind of have a little bit of intuition as why that's the case, why you have to add when they're in series, why you add as fractions when they're in parallel, right? Adding up multiple lines gives us multiple options, which lowers the resistance, okay? But other than that, just make sure you do the homework. And thank you for watching.